will implement a fib function that computes the nth Fibonacci number. It will be a recursive function. So here I will write the code on the left. On the top right you have the statement of the exercise, and below you will have the slides of the tutorial with here the first. For this exercise I will just put the reminder of how you call the procedure and what you do in the procedure when it's called. So first, when you write microcode, you have a main function that will call your function. I will not implement the main function here. I will just focus on writing a fib function. Anyway, you always have to include on top of your main function, that would be here, main instruction. So I include beta USM because I want to have access to all the macros that already are implemented in this file. That actually will make my assembler generate machine code for my fib function. So then you would have the main instructions, but I will skip that. I will just focus on the fib function. So first I define a label for the function, and this label will enable me to branch to this label and to call the procedure fib by going at this label. It's basically an identifier fib that says, okay, at this location in the code, you have the first instruction of the fib function. Then if you look at here, the first thing you do when you get in a function is that you save LP and DP on the stack. To do that, you have to push. That's how you put something in the stack. You push LP and you push BP. Here you can see I'm writing on the same line. It's okay to do that. It works. You can do that to reduce the number of lines in your code for some parts. Though I would advise not to abuse of this, because sometimes it might get a little bit difficult to read if you have too many macro invocation on the same line. Then I update the base of frame pointer of the current function, and I set the registers of that I will use for implementing this function. I know for sure that I will need one because I have one argument in this function and I will have to load it. And I'll certainly need a second one to manipulate and to execute the function, to store intermediate values, etc. So that's why I push R1 and R2 on the stack, because I will modify the value, and I want to be sure that when I come back to the function or the context that has called the function fib, I want those registers to have the same values as before the call. So I'm saving them so that I'm able to restore them at the end of the fib function. I've done that, so now I can load the arguments. To do that, I load from the base of frame, and I put the result in R1. Here I will load the argument n. And so if you look at the stack, so you have the base of frame, and then you have to go down to reach the first argument. So you have to go down 1, 2, 3 times. And if I multiply 3 by 4, because remember we have byte addresses and not word addresses in the beta machine, means that I have to access to BP minus 12 to access my first argument. So BP minus 12, the load will actually compute the address BP minus 12 and put the value in this address of the memory, of the dynamic memory, into R1. What you see here is a comment, obviously, and here also. When I've done that, I can directly dive into implementing the body of the function. I'm ready to execute it. So first, there is a comparison, and it's a less equal comparison. So I use compare less equal, which is, by the way, this one, CMPLE, of R of n, and I want to compare to 1, so it's a constant, so I have to use a constant version of this instruction. Compare less equal constant R1 less than or equal to 1, and I put the result in. I will put the result in R0. So why? If you remember R0, we have said, okay, this register can be used, must be used for return values. So it means that you cannot rely on on the content of this register to remain consistent when you call functions, because it's not saved and restored at the end of procedure because you need it to store return values. So you can always use R0 as a temporary register when you write in assembly code, because and I mean temporary register without saving it beforehand at the beginning of the function, because you know that because you use it to return values, you cannot rely on it to store value on the long run. So I'm using R0 here as a temporary register to store the result of the comparison. And then if it's true, I can branch to, if it's true, I can branch through R0 and I can go to another label, fib is base case. So it's a recursive function, and if it's true, I mean I can enter the if here, and it's the base case of the recursive function. So it means that below I will have to define a label if it is base case, and if it's false, it means that we won't branch and we will simply go to the next instruction. So I can implement the recursive case below. So we have to call Fibonacci twice and add the results. The first call must be on n-1, so I have to do r-1. So I use the sub macro using constant, and then I put the result in R0. I push that on the stack because it's the argument of the function, and then I can call fib recursively, and I set the second argument of call to 1 because I have pushed one argument, and it must be deallocated or removed from the stack when the function has been executed. Then I can move R0 into R2 because I have to. So when we execute Fibonacci, the result of the Fibonacci call will be saved in R0. Then you move R0 into R2 because we need it for the addition later, and the next call of Fibonacci will erase the content of R0, so we have to save it elsewhere. Then we have to call on R-2. I put again the result in R0. I push. It's very similar to the first call. I call fib1, and then I can add R0, which is the return of the second Fibonacci call, to R2, which is the result of which contains the result of the first Fibonacci call, and I put the result in R0. Why do I do that? Because it's actually my return, the value I want to return, so I can now save it into R0, and I should not modify R0 afterwards because it contains the value. Then I can branch unconditionally to the end of the function, so let's call it fib end. It's always good to prefix your labels with the name of the function when you write it, because it helps understanding as you write and as you read that you are still in this function. So now we have to implement the base case, and it's very simple because we have to return n, which is the parameters of the function that was stored in R0. So we put R1 into R0, and we have our base case. So now we have fib end, the last thing to implement. So if we go to the base case, after executing the move, it will go to the next instruction. So we don't have to branch to fib end because it will automatically go there. Here we get to branch to fib end, otherwise you would execute this move, which is incorrect for the function. So here it's the end of the function, so we have to reverse everything we've done at the beginning, except saving the return value. So, and we have to do that in the reverse order, obviously. So we had pushed value on R2 to save it, and we have modified R2, so we have to restore R2. We have to do the same for R1, which was saved. So it means that at this step, pop has removed from the stack the values we had pushed here. Okay. Then I don't have to move BP into SP because SP has been modified by the pop and has the same value as it reached at this one. So this one you don't have to repeat it because it's already done. You just have to be careful about this when you allocate local variables, because there you have change SP and you have to be sure to deallocate those local variables, otherwise it's fine. And then we pop the base of frame pointer and the linkage pointer of the calling function, and then we can simply return. So return, it's actually a jump LP. So we go to the we go back to the point where the calling function was interrupted, and we continue the execution of the calling function by going back to the instruction where it stopped. Okay, so that's all for fib. It's very simple function, and now you see how here how you can actually write assembly code, and how you implement the function. I've used few of the macros in the cheat sheet. Now I will display only the cheat sheet. So you can see return, jump LPR31. There is a call, there is a branch that I've used, branch true. You have push pop moves. So those are very useful and are used very often actually when you write our code. So it was exercise 1. Now you have exercise 2. So now we will re-implement Fibonacci, but in an iterative way. I will reuse the same labels. Normally you cannot use twice the same label, or it's bad practice to use twice the same label or more in assembly code. But now I will use it for the sake of the exercise, because the name of the function is the same, and it's the same function, just implemented differently. So, but remember, when you write a program, you cannot reuse a label twice. For this, we will have the same beginning, because we will actually push LP and BP, because you always have to save the context of the calling function. Move SP into BP. Then you push. We will use at least 2 registers, because obviously the function is more complicated. So we know that we will need at least 1 for the argument, and then maybe 2 more for the F0 and F1 variables here, and then we'll need maybe a last one for the temporary F variable in the function in the loop. So let's say we will use 4. When you write a more complicated code and you don't know how many you will use, maybe you can leave some space there when you write on paper, and if you write on computer, you can always go back and add more registers in this part. So the first thing we have is we initialize some variables with constant. So we use cmove to move 0 into F0. So let's say R2 is F0, and let's say let's move 1 in R3. R3 is F1. And finally, R4 is I. So now we can start the execution of the code in and by the way, it's 1 in the loop here. So the loop, how do you write a loop? So a loop, you will have a label. Why do you need a label? Because you need, when you execute a loop, you execute some code, then you have to jump back to the beginning of the loop, or to go out of the loop. So to go from a place in the code to another, we use labels to mark these places where you jump to. So we use a label for indicating the beginning of the loop. And the first thing you do when in a for loop is that you evaluate the condition. So here you have a compare less equal, not constant, a compare less equal, because you compare two variables. And you have I, which is R4, less equal to N, which I haven't actually loaded. So we load BP minus 12 into R1, so R1 is in. So I compare I to N, R4 to R1, and I put the temporary result in R0. And then I can branch conditionally. So if the condition is false, it means I have to go out of the loop because the condition is false. So I will write this. I will define I will define this label later. And then I'm in the loop. I can actually implement the body of the loop. We will first add R2 and R3 because it's F0 and F1. And put that in, let's say, R0. And then we can see move R3 into R2. And then see move R0 into R3. Because we do the addition, R2 plus R3, then we move F1 into F0, R3 into R2, and we move F into F1, which is R0 and R3. Then the body of the loop is finished, but we still have to increment the counter, so to execute the third part of the loop, and here we have to increment the counter of the loop. So the counter is R4, we increment it by 1, and we put back the result in R4. And then we have finished the loop, we have to go back evaluating the condition, so we can go back to fib loop. And that's how you write a loop. So you have the condition, you branch false, you go out of the loop, and then you write the body, you increment the iteration variable, and then you go back to the loop and do that. The end of loop part, we will simply move the result of the execution into R0 because the result is in R2. Yeah. If you look at the code, we return F0 and F0, it's in R2. Now that it's finished, we have to reverse what we've done above, so we have to pop R4, R3, R2, and R1 in the reverse order to restore the value of the register. Then you have to pop BP and pop LP, and then we can return, and it's done. So that's how you implement Fibonacci in an iterative way. The difference between iterative and recursive in terms of behavior in the machine is that when you do a recursive call, you have this push, you have all those things that this part of the function will be executed for every call, recursive call, so all those push will make the stack grow. That's why you can have stack overflows, because when you do a recursive function, every time you call the function, you have to save stuff on the stack, and you save stuff on the stack for every call. So the more recursive call, successive recursive call you have, the more elements on the stack. While with a recursive function, with an iterative function, you stay in the loop and you don't have all those calls. So that's all for the second exercise. So exercise 3, we will implement the sum function. And here we see that we are asked to use register for local variables. So instead of local variables, we use registers. That's what it means. So again, sum, you push LP, push BP, move SP BP. It's always the same. Then you save the register you're going to use. Here we have I, S, 2 variables. Then we have also N. So I suppose that we will need three registers. If I'm false, I can still correct it afterwards. I can load BP minus 12 to get the value of N, and I put that in R1. So I say that R1 gets the value of n, and now I can initialize my variables. So cmove ins, I put 0 in ins. Let's say R2 is I and R3 is S. Now I have a loop, a while loop. So while loop, I have to, as a for loop, I have to evaluate the condition before entering the loop. So compare less than R2 R1, because I compare I to n, but there is no 0. Then if it's false, I go out of the loop and I go sum end loop. If it's true, I can execute what's in the loop. So I can add the content of S, which is R3 with R2 with I, and then it's a plus equal, so I have to update S, so I put back the result in R3, and I have to increase the loop counter, so R2 I R2. And then I can branch to go back to some loop and re-evaluate the condition. Sum n, it's simply putting the result of the, so we return S is R3, so we put that in R0, and then we revert what we've done above. So pop R3, one, pop BP, pop LP, and then return. And we're done with the sum function without using local variables. For the exercise, I will just change it. Let's say to use only local variables. So if you use local variables, you cannot use let's say we have only one register available, and R1 and also R0. So to have local variables, you have to allocate on the stack a number of slots, a number of words that you will use. Here we have removed 2 registers compared to the first exercise, so we need 2 words on the stack, and they will be accessible by doing bp plus 0 and bp plus 4. And so let's say that bp plus 0 it's I, and bp plus 4 it's S. So how do you initialize those 2 locations? And so first, yeah, we load the argument into R1, which is our only available register, with R0. Then we have to initialize it, but we cannot just cmove, because cmove works between registers. So we have to use store, which is the instruction that allows us to write into memory. And store, it works like this. You first put the value. The value in this case will be 0, because we initialize the registers, the local variables to 0. And then for I, we said it was 0 plus bp, and for S, we said it was 4. So doing this, we initialize our variables with 0, because R31 contains 0. Then we get into the loop, and we have to load. So and we have it in R1, so it's fine, but we have to load the value of I, which is in R BP plus 0. So you load BP0 into R0, which is available, and you cannot overwrite R1. And you compare I to N, and you put the result in R0. And then you branch false on that. Then for the add, you have to get the value of S, load BP4 into R0, And you have to load also the value of I. So here we will have to overwrite the value of n, because we don't have a choice. We need to work on 2 registers and we have only 2 available. So we add R2, R1 and put that in R0. So in R0 we have now the result of the sum. And that we have to put back in S. So we have to store this value R0 into BP plus 4. And now, because we have overwritten the value n in R1, we have to load it back. So now R1 again contains the value of n. And we have also to increment, the value of R1, the value of I. So to do that, we have first to load it into R0, then increment it. And then store it back. And then we can go back to the beginning of the loop. Here we have to load, so the value of S, we cannot move it because it's not in a register, so we have to load it from BP4 to R0, and then we can just pop R1 because we haven't popped R3 and R2 here. But before popping, we pop R1 and then we deallocate 2 because we had allocated 2 here. Another option is to actually move PP into SP. It's equivalent. But I would say that if you use allocate, you should use deallocate because you can see the match and it's more readable. Then you pop BP, LP, and you return. So as you can see, this code is more complicated than the first because we have to go and go back into memory to fetch the values, and we have to store them back. And what you see here, this kind of pattern is actually what happens when you compile your code without optimization on GCC, I think. So on GC by default, it will all work mostly when you compile C code. It will compile it so that the variables are stored in the memory and not in registers. And if you enable optimizations, I don't know which step exactly with the -O flag, then it will actually try to use registers and be more efficient. So that was the version of exercise 3 with local variables. Exercise 4. Now we have this function, greatest common divisor. Let's dive into it. So we just have to translate it into beta assembly first. The beginning is always the same, push LP and push BP. Then move SP BP. Here we will need at least 2. Here we'll need at least 2 registers for A and B, which we can actually directly load, BP -12 into R1. So -12, it means it's the last argument we have pushed, so it's the first argument of the function. If we take the convention presented in the course, so it means that in R1 we have A. Then BP -16, R2, we have B in R2. First, now we can go into the function. First, the comparison, compare equal A and B, R1, R2. Put that in R0. If it's false, let's say if it's true first. If it's true, we go to this. It means that the greatest common divisor is A, and we don't have to do anything else. Otherwise, we have to check another condition. Compare. So here we have a greater then condition, which is not, which doesn't exist, but we can just reverse the arguments and use a less than condition. So compare less than R2, R1, and put that in R0. And if this is false, we go to GCD A less than B. If it's true, it means that the GCD must be computed by a recursive call. So we have to compute first A minus B. This is the first argument. This is the first argument. We always have to push the last argument first if we follow the course convention. So we have to push first B, which is in R2, and then we push the result of the subtraction, which is R0. And then we can call GCD recursively. We have two arguments that have to be deallocated afterwards, so we can set the second argument of call to 2 to deallocate them automatically. And when we've done that, the result of GCD is already in R0, so we don't have to move anything. We can just go to the end of the function. So now let's implement the other labels. GCD is A. GCD is A, so it means that we have to move A into R0 and we can go to the end. And then the last one. So now we have to again do a recursive call, except that we have to compute sub R2, R1 into R0, then push the last argument first, so R0, then push A, which is R1, and then call GCD with two arguments. And when we've done that, we can go directly to the end because R0 already contains the expected value. So the end is just reversing. At this point, at the end, we have already put the expected, the relevant value into R0, so we can just revert what we've done above. So we can pop R2, pop R1, pop PP, pop LP, and then return. So that's all for part A of the exercise. So now let's write the main function to call this code. So usually it's in, actually always it's in the main that you will include the beta USM file, and you don't have to include it in any other file if you include it in the main. Let's write the main function now. That's the B part, exercise B. The main, it always starts by including beta USM, obviously, because you need the macros. And then when you write a program, you have to do everything, because when you start the machine, all registers are set to 0, even the special one, and so you have to initialize everything that you need to run your code. So after the inclusion, what you need is to initialize the stack. So let's move stack into a stack. It will be the address of our stack that I will put here below. So I specify that my stack will be there, and I will insert all my code between the move and the stack. So the code segment will be up to there, and from the address of the address stack that will be contained in the stack identifier, I will have my stack that will grow towards higher addresses. Then I have to initialize the base of frame pointer of my main function. So the base of frame pointer is obviously the stack pointer, because it's supposed to be in the stack, and the stack is just empty at this point. And then my stack pointer and base of frame pointers are initialized, so I can branch to the main function. In the exercise, we are asked to define two global variables, and we will put them into the dynamic memory. We will have this 27x and y long 9. So it means that the identifier x, it's an address, and at this address in the memory you will find a long the value 27 written as a word. And y, it's an address, and at this address in the dynamic memory you will find a long 9 written as a word. And now the main, we have to load the values of x and y into registers because we need them for the execution. So to do that, you can either use load. So you know the offset is, you know you want to load something from this address, from x. But x, it's so you have to load x and R31, for instance. So x is the absolute address, it's the address of the long, so you want to do 0 plus this address and you get the expected value, and you can put that in R1. You can also use LDR, load relative, which will load relatively to PC, and then you don't have to add R31, so y and put that in R2. Both ways are correct, but you have less to write with LDR. And then you have to push. So let's push the last argument first. Y, push R2, then push R1, and then call GCD with 2. And then there will be a special instruction AL to stop the execution when it's done. And here you would include your code for the GCD exercise. So if you have your code in a file, the code above the GCD would be in this file, and you include it afterwards. It means that the code of the GCD file will be printed between the end of main and the stack. So when you start executing this code, it starts by the first instruction it encounters is the cmove, then the move, then the branch, then it goes to the load relative, push, and it calls the GCD, and it goes executing the GCD. When it's done, it stops on the alt instruction, which is a special instructions that you can use. Now the question is, how much memory is used on the stack for every call of GCD? So here, if we look at GCD, we have to see how the stack extends at every call, we have to check how many pushes there are on the stack for every call. So you always have for every call the arguments. There are 2 that are pushed before the call. Then you have push LPBP, 2 more, and then push R1, R2. That's 2 more. So you have 2 arguments, LP, BP, and 2 sub-registers, and it means that you have 6 words of 32 bits that are added on the stack for every call of GCD you execute. So it means that every recursive call you add 6 words on the stack. Exercise 4D, now you look at what's the state of the stack after you branch for the first time from the main to the GCD function. So what happens here is that you have pushed the arguments on the stack, last argument first, and then when you arrive before push, before the push LP here, so far you have just only 2 values on the stack, it's 9 and 27. So that's what the stack looks like when you first call it. Okay, exercise for E, what you do, we want to know what's the schema of the stack after the first recursive call to GCD. So you execute the GCD, you arrive here. For the 4D exercise, we stop there. So now we have 4 pushes. So we push LPBP. So we push LPVP, main LP, we have then main BP, and then we push R1 and R2 from the main. So for this, we check what are the value of R1 and R2. We start by pushing R1, and R1 we have 27 because it's X, contains X from the main. So that's the value from the main we want to save, because if we need again to use this value in the main, it should be the same value. And then we push R2, which is Y. Then we have finished initializing the function. So now AB, we start to execute, and we have to go up to the first recursive call. So A is different from B because we have 27 and 9. 27 is greater than B. So we match the first condition here. So now we can execute this. We are in this part of the code. So we do R1 minus R2, and it gives us 18 in R0. But first we push B, and then we push 18. So B it's 9. And then we have 18. And here it is, and here I have my stack. So after the first recursive call, I push the parameters, and I call, and I aim before the push LP of the first recursive call, and that's it.